Thanks so much for the introduction, Leon. As you said, my name is Peyton Shea, and I'm a postdoctoral fellow in the Department of Chemistry at MIT. Today, I'll be telling you about our work, supported through the Deshpande Center, on cleavable additives for degradable recyclable thermoset plastics to solve the challenge of plastic waste. Plastic waste is a problem of global significance, given the vast quantities that we generate each day. For many classes of plastics, recycling is bottlenecked by logistical challenges rather than technological feasibility. And the problem lies more in how we can effectively collect plastics to be recycled. For a major class of plastics called thermosets, however, which constitute 18% of all plastics made, the bottleneck is a technological one. Simply stated, we lack effective ways to break down and recycle these materials, even when we have collected them. As a result, these plastics, which are used in environmentally friendly applications such as turbine blades and wind energy, must simply be buried in landfills or incinerated. The amount of plastic that we are generating is projected to triple over the coming 3 decades. New technologies to tackle the challenge of plastic waste should not only focus on developing entirely new classes of plastics with recyclability built in, but should also focus on addressing the existing classes of plastics that we use today. Our approach focuses on new ways to endow degradability and recyclability to these existing classes of plastics to head off this growing plastic waste challenge. We have developed an approach to enable the recycling of thermosets through the use of novel chemical additives. Thermosets stand in contrast to many household plastics, which are defined as thermoplastics. These include polyethylene, used in plastic wrap, and polyethylene terephthalate, used in plastic water bottles. Thermoplastics are not cross-linked, so these materials can simply be melted down or dissolved in solvent and remolded for recycling. In contrast, thermosets bear additional chemical crosslinks. These crosslinks make these plastics resistant to melting and dissolution, which is ideal for high-performance applications requiring good temperature or solvent resistance. But this also means that thermosets cannot be recycled like thermoplastics. Our approach involves the development of novel chemical additives. These additives have unique properties that enable us to introduce cleavable bonds at precise locations within the thermoset network. By controlling where we introduce the cleavable bonds, we can minimize the amount of additive needed to break down a thermoset into soluble fragments that can be used in recycling. Our approach requires no change in manufacturing workflow beyond blending in our additive before curing, and results in no change in material properties, owing to the low amount of additives we now need. In one example, we have validated and published on our approach to endow degradability and recyclability to the thermoset polydicyclopentadiene, or PDCPD. PDCPD is a billion-dollar-a-year material and is suitable for a variety of different manufacturing methods, such as reactive injection molding, 3D printing, as well as low-energy curing methods, such as frontal polymerization. PDCPD is prepared by the polymerization of DCPD. Like other thermosets, PDCPD is connected through carbon-carbon bonds, owing to the mechanism of polymerization and curing. As PDCPD is connected through these stable linkages, there's little we can do to break these materials down short of burning them. An example of an additive we have developed is shown here, a cyclic compound that contains an oxygen-silicon-oxygen, or silyl-ether linkage. This additive copolymerizes with DCPD under standard curing conditions to introduce cleavable silyl-ether bonds in the PDCPD network. The resulting material has identical mechanical properties to native PDCPD, but can now be dissolved on demand to generate high-quality PDCPD fragments and to recover high-value embedded reinforcing materials, such as carbon fiber. With the help of the Deshpande Center, we have initiated collaborations and material transfer agreements with multiple PDCPD formulators and end users. Moreover, we have scaled up our approach and secured kilogram quantities of our additives to support these collaborations. Thermoset materials are used in a variety of areas, and we are excited about the opportunities to make an impact in this space. For example, there are other classes of thermoset plastics beyond PDCPD that are amenable to our approach with the right additives. In addition, thermosetting materials are also found as adhesives and coatings. Simple ways to break these down and remove them on demand can help manage end-of-life product disposal. Our approach of making degradable versions of these existing materials can offer tremendous value to organizations striving to reach their sustainability objectives. Through our conversations with industry veterans across the infrastructure, coatings, and automotive spaces, we have received universally positive feedback on the potential of our technology. With the support of the Deshpande Center, we are excited to tackle these different areas, utilizing our core strength in novel additive discovery to address this global challenge of plastic waste. So on behalf of my team, which includes Keith Husted, Professor Jeremiah Johnson, and Professor Rafael Gomez Bombarelli, with expertise across experimental and computational materials discovery, I just wanted to thank you for your time and attention, and I'm happy to talk more in our breakout session.